In this session, I will discuss basic concepts of CPU scheduling. Let's start. First, we will discuss what do we mean by CPU burst and IO burst. Maximum CPU utilization is obtained with multiprogramming. How? Several processes are kept in main memory at one time in multiprogramming. When one process has to wait, then the operating system takes the CPU away from that process and gives the CPU to another process. This pattern continues. Every time one process has to wait, another process can take over the use of CPU. In this way, the CPU is not sitting idle, it always has some process to execute. So, in case of multiprogramming, maximum CPU utilization is obtained. And in order to select the process from main memory that can be allocated to CPU, we need CPU scheduling. It is the job of short-term scheduler. The success of CPU scheduling depends on an observed property of processes. Process execution consists of a cycle of CPU execution and IO wait. Process alternate between these two states. It is important to note that process execution always begins with the CPU burst. So it will always be first allocated to CPU, then it will be executed by CPU for some time, and then it may be followed by an IO burst. Means the process may need to go for some input output, as you can see in the diagram. Again, after completing input output, it will be again allocated to CPU. So there will be another CPU burst. Then again there will be some IO burst and so on. Eventually, the final CPU burst ends with the system request to terminate the execution. The durations of CPU bursts have been measured extensively, although the length of CPU burst varies from process to process. But a curve has been plotted, which is generally an exponential or hyper exponential. In this curve, we will see processes which have shorter CPU bursts. If you can see, this x-axis shows the CPU burst duration and the y-axis shows the frequency. So you will see that these are the processes, this peak, these are the processes which have their burst within 0 to nearby 0 to 8 milliseconds. And after that, this line shows the processes for which they have longer CPU burst. Generally, the processes which are IO bound. Remember in the last session, I told you that IO bound processes are those processes which need more input output than CPU. So those processes will be plotted here, somewhere here. So these are IO bound jobs. And CPU bound jobs means they have long CPU bursts. So these processes will come in that category, CPU bound programs. Now let's discuss CPU scheduler. Whenever the CPU becomes idle, it means the process that CPU was executing has gone in waiting state. It needs some input output. Then the operating system will select some process from ready queue, right? And it will allocate that process to CPU, right? And this selection process is done on the basis of some criteria, and it is carried out by short-term scheduler. This scheduler is also known as CPU scheduler. The ready queue can be implemented as FIFO queue. FIFO stands for first in, first out. We will discuss these queues one by one later. Next can be priority queue. It can be implemented as a tree, or it can be simply any unordered linked list, right? What is meant by storing a process? Storing a process means keeping the record of a process, and the records are kept as in process control block of the process. Every process has some information, and that information is stored in its PCB. That information can be its ID, CPU scheduling information, memory management information, and so on. You can refer to previous slides. We have already covered process control block. Now let's understand dispatcher. Dispatcher is a module that gives the control of the CPU to the process which is selected by short-term scheduler. The module is termed as dispatcher. The functions of dispatcher are switching context. What do you mean by context? Context is state of a process. Switching means initially the state of, suppose P1 was saved on CPU, and if P1 has to go for some IO, then state of P2 has to be loaded on a CPU, right? Switching to user mode. Say there are two modes of operation. One is kernel mode. In the previous chapters, you must have covered this kernel mode and user mode, but just I'll give you a quick revision. Kernel mode and user mode. When operating system is operating in kernel mode, then it is doing system related functions. System related functions. Like, for example, if you're changing properties of your system, like you're changing date and time, all these operations, these will be done in kernel mode. User mode. User mode means all the rights which are given to a user program so that it can execute. There will be some functions which cannot be performed by the user, like IO functions. So those functions can done only in kernel mode, and there will be some functions that can be performed in user mode. So the C system switches from kernel mode to user mode. So again and again, the operating system keep on switching from user mode to kernel mode and kernel mode to user mode. So this switching is done by dispatcher module. Another function is jumping to the proper location in the user program to restart that program. Again, come to this example. Suppose P2 has to go back to go to IO, and in the meantime P1 is free, right? P1 has completed his IO. Now scheduler will select P1 to allocate it to CPU, but CPU will not execute P1 from start. It will execute P1 from a particular location. And yes, tell me where from where the it will start executing the next instruction. The address of next instruction is stored in, yes, program counter. And the module of operating system that handles this jumping to proper location in user program to restart that program is handled by dispatcher. Okay. Now let's see what is meant by dispatch latency. See, switching from one process to another process, jumping to a program to a particular location, switching from user mode to kernel mode, it is not done in zero time. There will be some time which will be taken by dispatcher to do this work, right? And the time that is taken by dispatcher to stop one process and start another running means switching the state from one process to another process. The time that is taken by dispatcher to do this is termed as dispatch latency. Different CPU scheduling algorithms may have different properties, and the choice of a particular algorithm may favor one class of processes over another. In choosing which algorithm to use in a particular situation, we must consider the properties of various algorithms. Many criteria have been suggested for comparing CPU scheduling algorithms. Which characteristics are used for comparison can make a substantial difference in judging that which scheduling algorithm is best. So now let's have a look on the various scheduling criteria one by one. First, we will discuss CPU utilization. We all know that we want to keep CPU as busy as possible. Conceptually, CPU utilization can range from 0 to 100%. Means you can use CPU between 0 to 100%. In practically, the CPU utilization must lie in the range of 40% to 90%. So 40% for a light loaded system and 90% for a heavily loaded system. Next criteria is throughput. If the CPU is busy executing processes, it means some work is done. We can measure the work in terms of number of processes that complete their execution per unit time. So this factor is known as throughput. For long processes, the throughput may be one process per hour, and for short processes, it can be 10 processes per second as well. Okay. Next is turnaround time. From the point of view of a particular process, the important criteria is how long it takes to execute that process. The interval from the time of submission of a process, and the submission of a process is considered in, I told in previous session, in main memory, right? The interval from the time of submission of a process, right, to the time of completion, means to the time it is terminated, it leaves the CPU. That time interval is known as turnaround time. And it is the sum of all the times that a process spends in the system. Like, it starts with the time when it arrives in the main memory, then it may be waiting in the ready queue, so waiting in ready queue, plus the time it is executing on CPU, that time, plus the waiting time that it is doing input output. So all the times, if you add up, you will get turnaround time. Next is waiting time. Waiting time, now the CPU scheduling algorithm does not affect the amount of time during which a process executes or does input output. So we always consider the waiting time as the amount of time a process has been waiting in the ready queue. We always consider this waiting time for input output as negligible. So this waiting time is the amount of time a process has been waiting in the ready queue. Next is response time. In an interactive system or time sharing environment, turnaround time may not be the best criteria because it gives us the time when it was submitted and the time when it was completed. So response time is something like when a process produces its first response. That might not be the complete output, but that can be the first response which is produced. So that measure is known as response time. For example, if you're trying to load a web page, you write on your web browser, like say open.com, something you write on your web browser. So when the page is loaded from server, you're not able to see the complete page. Few portions of the page are visible in durations of time. So the very first content of the page that was visible to you. So the time interval from you write something to open in browser to the time some content appears, that time will be considered as response time. We have discussed CPU scheduling criteria. Now we will discuss that which criteria we want to maximize and which criteria we want has to be minimized. So we all know that first criteria was CPU utilization, and so the objective is to maximize it. Another is throughput Throughput is the number of processes completed per unit of time. And for efficient utilization of system, we would like to maximize the number of processes completed per unit of time. Turnaround time. Turnaround time is the time interval from the time a process is submitted to the time the process completes. And we want this time to be minimum. We want that the process completes quickly. So this time has to be minimized. The objective should be to minimize it. Next is waiting time. Waiting time is the time that is spent by a process in ready queue. So we want that the process should spend minimum time in ready queue. It should be quickly allocated to CPU and complete its execution. So the objective is to minimize waiting time. Again, response time is the time from which the process is submitted to the time the first response of the process is produced. And we want to see a quick response of a process. So the objective is to minimize response time. So this was all the optimization criteria. We want to maximize CPU utilization and throughput, and we want to minimize turnaround time, waiting time, and response time. So these were the basics of CPU scheduling. In the further sessions, we will discuss the algorithms one by one. Thank you.